So going into magnetic properties, um, I have discussed last time, right? So where this magnetic properties arise, right? Magnetic behavior, magnetic fields, and so on and so forth. So again, I will give not total description, but wherever the sir has missed. Okay. So those things I will discuss today. Right? Okay then. So we all know from where the magnetic field arises, right? So magnetic field arises from the atoms. The magnetic field actually arises from the three things. Okay, the first one is the electrons, and the second one is the neutrons. These two things will give you your magnetic field. Okay, so electrons is nothing but it should be a pair of electron and proton. Okay, I shouldn't say only the electrons, because the orbital magnetic moment involves the proton also, right? Because you need plus and minus for a current loop. I mean, for physical distinction you need protons, but actually if you see, it's all about electrons and neutrons. So you have now how do we define? We define it as magnetic moment right, magnetic moment from electron. So magnetic moment is electron, right? So this is my electron. Now if I say magnetic moment is coming from an electron, then it is coming from the two parts. One is from orbital, and another is from the spin, which is the intrinsic spin. Just like the earth moves around the sun, that is one motion, and the earth moves around itself, like rotates around itself. So that is another motion that we called as an intrinsic spin. And intrinsic spin we define like quantum numbers. We define plus half and minus half. That means either you have a up spin or down spin, right? So we have defined a magnetic moment from the orbital, right? So magnetic moment from the orbital, and that is called as an orbital magnetic moment, which we give as ml. And another thing we have ms, the spin magnetic moment, the orbital magnetic moment and the spin magnetic moment. And these are some quantum numbers that we define. Okay. Now there is also the magnetic moment from neutron, but because it is very less when compared to the electron's magnetic moment, so we just neglect it most of the times if we are talking about bulk atoms or anything. And if you are talking about only few atoms, then you need to consider the spin magnetic moment, right? Yeah, just like the law of average numbers. If you have large numbers, then you can just neglect the small numbers, right? If you have if your system is very small, you cannot neglect your small numbers. So I hope that thing is clear. Okay. And after that, yeah, and magnetic moment we have defined, right? So mu b dot b, if I am talking about energy. For example, if I have an electron and it is inside a magnetic field B, then what is the energy associated with it? It is mu b dot b, and mu b is coming from my electron, either it is L or S. And for this we define and so you have your L, the magnetic moment coming from your orbital, and you have your S, the spin magnetic moment, which is coming from an intrinsic spin. Now how do the total magnetism happens? Like what is the total magnetic moment? So here the term comes, here there are two types. One is your what do you call it? Yeah, LS coupling the two type of coupling. Now how these two will add or subtract, right? So you need to understand. So it's not very simple, like straightforward in quantum mechanics. You cannot just say, oh, you have L and S, you just add them or subtract them. No, because L has different numbers. L has like, for example, if I'm talking about p orbital, then I can write 0, 1, 1. If I'm talking about d orbital, then -2, -1, 0, +1, +2. So L has different numbers, ml. And same goes for SL. SL will have what? Your plus half and minus half. Right. And there is LS coupling and there is also LL coupling. Now what is the difference? So whenever we talk about LS coupling, right, whenever I talk about the LS coupling, so these LS coupling mostly happens in D block elements and LL coupling mostly happens in F block elements due to the electron shielding, right? So I will not discuss those things because that is again out of the scope for this lecture. So basically what I'm trying to say is how the magnetism is coming from. That's we are only focusing on that, right? We will not go very deep. We will not stay on the surface. So it's like more of scratching the surface, right? Okay then. And yeah, so far you understand the magnetic moment is coming from your orbital magnetic moment and spin magnetic moment. Now, how do this? Now, what is the resultant magnetic moment? So that's our question. So we have two types of magnetic moments coming from an electron. Now, what is my resultant magnetic moment? My resultant magnetic moment comes from how these L and S values are adding or subtracting. That's the only part. Okay. So there are two cases in which they add or subtract. One is the LS coupling, another is the LL coupling. Coupling is nothing but you just in quantum mechanical way you are adding. That's all. That is not very, I think. Okay. Now in LS coupling what happens? So all these L values of all the atoms will first add themselves. So whenever I'm talking about LS coupling, so L is nothing but my orbital magnetic moment, right? So in an atom, each electron will have specific quantum number. They will not have the same, right? We all know that. Each electron will have a specific quantum number. Whether it is S, I mean, if you have S orbital, what is the orbit? Then orbital, what is its orbital magnetic moment, and then is spin magnetic moment. So you have N, then you have L, then you have ML, and then you have MS. So each electron will have a specific quantum number, right? They will not have same. Please bear this in mind. So each will have some ml value. Each electron in atom will have ml value, and these ml value will first gets added. Only mls, right? Please remember, I should write it in small in subscript, right? Please better understand. Yeah, ml. Let's say this is 1, ml2, this is ml3. Okay. Not square, it is a number. Instead of writing like that, let me denote L as subscript. That will be very much understanding. ML, ML1, ML2, ML. So first L. So all these values will get added up for all the electrons. Then you will have a resultant L. Same goes for spin. All the MS values will get added up. Then these things will. Then you will have a resultant number. You will starting with. So you start with L minus S minus 1 and so on, and then you have L minus S, L minus S plus 1. So you will have different values, right? And if you add these vectors, you will have something like this. You have some summation of values, right? So you will have this summation of values, right? So here I might have L minus n 1, or here I minus have L minus 2, or here I minus have L minus s, L minus plus 1, L minus. So these are the values I may have. Right, these are a set of values, and these are the set of magnetic moments that an atom will certain atom will generate. Right. So this is about LS coupling. Now what about LL coupling? This happens in F block elements because the shielding and so on and so forth. So in LL coupling, the thing that happens is first the LS, ML1 and MS1. These things will first get added. Right. There first all the orbital magnetic moments will get added up, all the spin magnetic moments will get added up, and then they will start having values. Then they will generate some values. But here that's not the case. First the L and ML value, MS value will get added up. Then you will have certain values. Then again you will have summation just like this. So that is the difference between LS and LL coupling. These are two different types of coupling depending upon these were generated depending upon the energy values of the electrons. Okay, so you can just read about it. They are not very difficult. All you need to, if you want to go mathematically, yeah, then it will get a bit tough. But if you want to physically have a little grasp, then all you can just see is Wikipedia. There, the information is enough to vaguely understand what is LS and LL coupling. Okay, so this is where the magnetic moments come from. That's why, and there is another thing called the molecular MOT, molecular orbital theory, right? So sorry, the density of states, where whenever the molecules, just like I have said before, these orbitals will overlap and they will form bands, conduction band and valence band. So for example, let's say an atom which has, let's take a material which has a band like this and there is another band like this. Okay, now why I am drawing a central line here? Because apart from this line, after this line you will have plus half spins, the electrons with plus half spins, and before this line you have electrons with minus half spins. Same goes for you, plus half spins, minus half spins. This is the density of states. This is how the orbital distribution takes place. And then let's say I define this is my, above this I have a conduction band. Let's say these are metals. Okay, let's not take metals. Let's say some type of material where above this you have a conduction band. Okay. Now this is my, again the same, I will draw. Now what happens if I apply magnetic field? Let's say I have applied magnetic field, B or H. So if I am talking about vacuum, then I will say H. If I am talking about, if I am more or less I am saying about a medium, then I will take B. Okay. Now I am trying to apply magnetic field. Now what happens? So I have explained before, whenever you have an magnetic field, then you will have an associated energy with your magnetic moment. UB dot B. You have UB dot B. Now what happens? Mu B, that means the magnetic moment. And if you are talking about spins, then you have half. Okay. Mu B of maybe I could take magnetic moment of S. Right. So I will write it as MS. I will write it as MS. Okay. Then if I have half, then it will be plus half, and plus half MS time dot B, it will be positive quantity. Now what about if I have a negative half, negative spin, minus half spin? Then my energy will be E will be minus mu B dot B. Why? Because I have minus half there. It's not a plus half. MS value will be minus half. Then my energy value will have a negative value. Right? So if I apply magnetic field, right, now what happens? This will shift upwards. Why? Because it is a plus half. Right? Plus MS dot B. It will shift upwards. So it will shift upwards a bit. Now what happens to this guy? This guy will shift downwards. And this is your E1 plus E2, which is from plus half and minus half. That's it. Now whatever the electrons which came above the conduction band, this will give us the M saturation, or not M saturation, the magnetization. Only those electrons which are above the conduction band will give you the magnetization. But what about the below? They will not, because they are below the conduction band. The same happens for this guy also. One guy will move up, the another guy will move down. The same, half and E from minus half. Right. That's why whenever you see the actual magnetic moment of iron, which we always see, there is this formula in 12. All we did was, what is the magnetic moment of iron? We just count the D, which how many lone pairs are there. So the iron has how many? I guess 4, right? Yeah, iron has 4. So that's why we always say, which is 4 mu B dot B, which is not the case. Because when you actually measure the magnetic moment of iron, it is somewhere like 2.2, like it is not an integer. It is a rational number. Right? And the reason why that rational number comes is because of this guy. Okay, so those electrons which come above our conduction band will give you the magnetization. That's why, and that value is not integer value, right? You cannot say this many number of electrons. So when you say this many number of electrons, it will become a rational number, just like the Avogadro number, right? It's not an integer. I mean Avogadro number is an integer, right? Sorry, my bad. So because it is 6.02 into 10 to the power of 23, so it is a fixed number of atoms. But whenever I say that, means half is not your integer, right? Because MS value is always half. It will not change. When you take a magnitude, it is half. It may change like plus half, minus half, but the magnitude is half. It will not change. So that's why when you try to multiply it with these guys, the amount of electrons that are coming out, that will be your integer value. So that's why whenever you try to actually measure the magnetic moment of iron, it will not be 4 mu B. It will be some integer, like it will be some rational number, like 2.2, 2.4, 2.5. So now you will know how that is coming from. And this 4 mu B is like more classical way of explaining the magnetism. And we all know the classical thing will always fail whenever we are talking about magnetism, right? Magnetic moments. Okay, so that is about the magnetism part, which is coming, how the magnetism is coming from. Then coming to the magnetic fields in vacuum. Now how do you measure the magnetic field, right? So that's why people came with a term now. So whenever you have a current carrying loop, so whenever we talk about the magnetic fields generated we talk about H, or you will try to say. So the generated magnetic fields are represented by H. So generated magnetic fields are denoted by H. Right, for example, if you have a current carrying loop, right, then the magnetic field is my current, then the magnetic field generated by it will be, let's say this is the dot position, right, upwards. You have right hand thumb rule. When you apply right hand thumb rule, then it is curling anti-clockwise, so the magnetic field is coming out of the screen, so it is dot. If it is going into the screen, then it is a cross. It's just an arrow. When you see an arrow from front, it will look like a dot, and when you see an arrow from back side, then you will have those feathers, right, feather like things. It will appear as a cross. So that's the deal with dot and cross here. And then you apply Ampere's law. Ampere law will tell you the mi upon n, it is n. You can take anything, n or n. So we already mentioned m, right? So let's take n now. N is nothing but the current number of loops of current carrying conductor. If you have 2 loops, then it is n is 2. 1 loop, then it is 1. Right? And I is my current density. Okay. So my H is ampere per meter.
Hello?
Ampere per meter. Okay. My H is ampere per meter. That is my unit. That's it. Now, and we know that H is my, because I am representing as an ampere per meter, then that means my ampere is, you can take it as a scalar quantity, and m, you all know distance displacement is our vector quantity, so our H will finally be a vector. So it will have both magnitude and it will have direction. So we represent it as a vector field. And also we also know that in in motors, how this thing happens. The magnetic field exerts force on a wire carrying electrical current, right? So there is this generation of a dipole moment. So I will not explain all those things because this is all covered in plus 12, right? Plus 2. Now, so the magnetic moment will be given as I into area of the current carrying loop. Okay. So this is the magnetic moment. This is what we have been deriving from last. In last lecture also we have derived for this current carrying conductor loop, right? What is the magnetic moment from current carrying loop? It is nothing but the current into the area. The current carrying loop times the area. And I is my current density, which is current per unit area, and it is ampere per meter square times my meter square will give me the magnetic moment. Right. So yeah, then the units of m is actually ampere per, no, not ampere, it's ampere dot, no, it's just I is nothing but current, so times area, then it is ampere per meter square. So please remember this units, because when we try to like denote the other magnetic field like B, it will be useful. So we all know what is H. H is our magnetic fields created by like electric charges, electromagnets, electric spins, anything that creates magnetic field, we denote it as H. Okay, so yeah. Then if the loop is placed at right angles to the field H, it feels a torque. And how that feels a torque? Now let me explain. You know what? Let's explain everything, because it will be a little bit confusion if I do not say a few terms, right? So first thing, we have a magnetic moment. We have a current carrying conductor. Okay, so let's say my current is flowing in anti-clockwise direction, and because of that, the magnetic field is coming out of the screen. Okay, and this is the top view, and if you see the side view, then the circle will look like a line because it is a two-dimensional thing, right? And the magnetic field will look like this. This thing out. Yeah. Okay, so you have your magnetic field in this direction. This is the magnetic field this current carrying loop is generating, H. Okay. Or I can say I shouldn't write H, it is magnetic moment, right? This is M. This is the magnetic moment that it is generating. Okay. Now what I am trying to do, I am trying to apply a magnetic field, H, a separate magnetic field. Okay. So what happens? These two will interact, and because of that, you will have a torque, which is given as mu naught M H. Okay. So you know torque units, right? It is force per. It's not force per. It is Newton meter, right? Because torque is F dot R. So torque should be Newton meter. Now, you know what is unit of M? M has units of ampere per meter square. No, ampere meter square. Ampere meter square, and H has units of ampere meter. So meter will get cancelled, and you have ampere square, right? So ampere square times meter, and then you have some proportionality constant, which is mu naught, and then mu naught should have mu naught, right? And we all know what is mu naught. Mu naught is permeability of vacuum, which is equals to 4 pi into 10 to the power of minus 7, which is given in Henry, so Henry per meter. Now, and because to define all these things, we invent some other magnetic field, because to define this guy, to define let's say to link these, the torque, so we define a second measure of magnetic field, and one that relates directly to the torque, so it exerts on a magnetic moment, right? And it is called the magnetic induction or flux density, right? So then the B will be equals to mu naught times H. So you can see what is the difference between this equation and this equation. So this equation difference is torque per magnetic moment. And what is the torque? Torque is nothing but torque I have Henry per meter times, and then I have Henry per meter, and then I have magnetic moment ampere per meter square times ampere per meter divided by ampere per meter square. This guy will get cancelled. So and then finally you have units of Henry dot ampere per meter square, which is also equals to 1 Tesla. So a magnetic induction of V 1 Tesla exerts a torque of 1 Newton meter on unit dipole at right angles to the field H. That's it. That is what it means. Okay. Now you know you have V to define your torque and magnetic moments. Okay. So whenever you face with the interaction, or for example, see whenever you are trying to say, okay, there is this field in a vacuum or inside a material, you say H. So something is generating a magnetic field, then you say magnetic field intensity, that is H. Now when does this B come from? When you add B, whenever there is an interaction between something, some M or some electron and some your applied H. Okay, then you will say, yeah, you should take B, because that's what we have defined so far. Now let's say, now again, when do you use B? Okay, if the space inside the coil wherever we are generating the magnetic field, okay, so is filled with the material, just like in transformers. So you have your transformer core and then you have your windings. You apply some current, then you will have the magnetic fields. Magnetic fields going like this. Right? Now, I have a material inside. So if this is my material, if I have inside my magnetic field, then the atoms will respond to it, right? Before that we only have a vacuum, because that's what we have been talking about. You have magnetic field generated by something which is in a vacuum. So again, you now understand where the H is being used, right? Now whenever there is a involvement of a material, then the material will have atoms, then the atoms will have some magnetization, right? So our total magnetic field will be given as mu naught M plus H. Right? And people even say that M and H are independent. No, they cannot be independent. Why? Because you are applying your H, and with that your M is changing. M is coming from the atoms. Atoms, I mean electrons. And electrons will react only when you apply something. And your application is this magnetic field, which is coming from either you are generating it from current carrying loop or from any other type of things like piezoelectric or any other magnetostatic materials. It doesn't matter. It all depends is atoms have electrons and electrons have their respective magnetic moments, and these magnetic moments can be altered only if you apply the magnetic field H. Right? So that's why you write it as M or H, and M on H are mostly dependent because they outside they may look they are independent, but actually they are dependent. The two are coupled. You can even say that. And if the material is and depends upon what type of material. If it is ferromagnetic, then there will more coupling because ferromagnetic will interact more with the magnetic field. If it is a diamagnetic, it will not, and if it is a paramagnetic, it will react less. Right? And to define this interaction, we define a term called this guy, and this guy is magnetic susceptibility. And this guy will tell you how strong the M and H are interacting. That's it. That's the only job for this term. Susceptibility will tell you how strong the M and H are interacting. If it is a ferromagnetic, susceptibility will be very much greater than 1. If it is paramagnetic, it will close to 1 and 0. It will lie between 0 to 1. And if it is diamagnetic, it will be negative value. That's it. So that is the job of susceptibility to tell us. Right? And if somebody asks what is the difference between ferromagnetic and paramagnetic, you can just tell them, so this is the susceptibility number. You can just see the susceptibility number and you can know, yeah, this is the ferromagnetic and this is the paramagnetic. That's it. Now, okay, if everything is good, now how do you measure? That is another thing, right? How do you measure these things? So there is one very interesting characterization technique for magnetic materials, that is MH curve. You all know what is MH curve, right? It's been repeating from like what, +9 +8, I don't know. From there it's been repeating what is our MH. So it's a very down to earth simple diagram, right? So there is this application of H, you measure M. There are different things. You have VSM, vibrating scanning magnetometer, which is nothing but you have two strong magnets, and then you put a sample here and then you start vibrating. And because of the Faraday's law, and you know the Faraday's law, whenever there is a change in magnetic field, whenever there is a change in magnetic field or current or the area of the loop with respect to the time, you will generate some electric current. So with that electric current, you will find what is the magnetization. That's it. That's what we do in vibrating scan magnetometer. So how do you do that? So for example, you will have very thin strip. You put your sample here. You have very strong magnets facing north and south pole. So you have a magnetic field, and you start vibrating your sample up and down. And because of this vibrating, there is change in magnetic flux, and the change in magnetic flux interaction with your material will generate electric current, and this electric current is then that electric current is very low, so this current is fed to some amplifiers and they will amplify your current, and then you will have your magnetization value. And for that, that's it. From electric current, you can directly tell me what is the magnetic moment, and from magnetic moment you can tell me my magnetization, which is magnetic moment per unit volume will give you the magnetization. That's it. Right, so that's it. That is how you do in VSM, and there is very high level things for very strong magnetic field like 12 Tesla, 10 Tesla for very good, like very ferromagnetic materials. You need very high magnetization you need very high magnetic fields to saturate, to reach MS, right? So yeah, that is about squid. That is mostly about the semiconductor thing. Let's not discuss that because that is very, very much complex to not to understand, to explain for me. Okay, VSM is very easy, and it's been using from like starting to measure the magnetic property. Okay, so yeah, and it is also not very robust. No. Okay, now, so for example, if you have some like ferromagnetic material, then it will have some saturation. So you start applying your magnetic field, the magnetic saturation will rise and it will reach a constant value, that is the maximum saturation that you can obtain in your material. That means all the spins in your material is facing up, I mean facing in the direction of magnetic field. That is the maximum you can obtain, and that is the M saturation. And then you start decreasing your magnetic field. It will follow this path, but it will not follow the initial path. Why? Because now the magnetic moments will start getting randomly arranged, and then they will reach when h is again 0. They will again reach some value, and that is ms. Not ms, that is mr, or remanence. The remaining magnetic moment that's been remaining in your material. If it is a ferromagnet, then it will be very large, and when it is a paramagnetic, then it will be 0, because the magnetic moments will cancel out, will randomly get aligned in a paramagnetic material, right? So that's it. And to make this MR0, to make this totally non-magnetic sample, you need to apply the magnetic field in reverse, so that the magnetic field lines will start cancelling out. Okay, and M will reach a value 0, and this is your HC. HC is nothing but the coercivity. That means the maximum, I mean the magnetic field that you need, that is required to make your ferromagnetic material reach an M value 0, or make in walk way make your magnetic material to a non-magnetic material. That's it. I shouldn't say non-magnetic material, because whenever you again apply magnetic field, it will become magnetic. It is like making M value 0. That means if you take any pin and come close to your magnet, that pin will not get attracted to that. That's it. That is what we are doing. Now if I again reverse, see HC, not HC. What do you mean by positive and negative values? Positive is nothing but if I have a material, if I am applying in this direction, that is a positive edge, and if I am applying this in this direction, I am keep on increasing that, then that is taken as negative direction. That's it, no difference. Now if I try to again increase my HC, the M value will again rise, again it will reach a constant. Now all the spins are facing downward direction inside the material. Okay, again I will start decreasing, go like this, same, you will have minus MR. Now if I want to make 0 in the opposite direction, now all my spins are facing down direction. I do not want that, I want to make it 0. Okay, so and to make it 0, again to make it not very much interacting with any other indices, what I will do is I will increase this guy, I will again reach the same value. It will reach the saturation. Okay, so this very humble MH curve, that's what people used to say, and then you will have minus HC here. So it is positive MR and it is negative MR. So in most of the experiments, this HC will not be constant here. The same value will not be here, because of some sample geometry, or the sample placement inside the magnetic field, or the magnetic field direction itself. So yeah, there are many things that will affect. So this curve will slightly shift either left or right depending upon your shape, or it might even move up and down. Okay, so it happens in most of the materials. And for that you need to have a very perfectly cylindrical round sample, which is very difficult to make, which is not possible, right, for every material. If you are trying to measure, for example, if you are trying to measure the magnetic property BH curve of NDFB magnets, which are very strong ferromagnets that we have, the world is using right now, and you cannot make a very perfectly cylindrical round sample, right, because those are very brittle, and it is very hard to make. Okay, and instead of that you can just cut a very not even cuboid sample of that, and then you do the testing and you will get average values. All you do is, if you have a different HC values, then all you do is HC1 plus HC2 upon 2. You just take the average. The same goes for magnetization. You just take MR1 plus MR2 upon 2. You will have the average values of HC and MR. That is one thing, and the other thing is your energy product is nothing but the energy under this guy. Okay, you just do the integration, you find the area that will give the total energy of that's being used to do this curve. Okay, so that is one thing, and yeah, that is all about the image curve. Okay, now what else is remaining? I guess that is all about the magnetic properties, right? Yeah, and there is this another term called block wall. So block wall is nothing but you will have orientation change. So that is what happens in a block wall. So you have up spin and then you have down spin, and how this spin, it will not drastically change from here to here. This is how it will change. It will create a wave. See, it is more like a helical path, like DNA. So that is how it looks like. And when you try to add all these magnetic moments, when you try to add all these magnetic moments, it will turn out to be zero, because the vectors will arranged in such a direction. When they do the summation of magnetic moments, it will result in zero magnetic moment. See, if you see here, this guy is in this direction and this guy is in this direction, and they will cancel out. They have same angle, they will cancel out. And then this guy is in this direction and this direction. See, the horizontal even the horizontal components will also get knocked out, right? So that is about block wall, and sir has also discussed this part, right, where there is a single domain, and there is this other term called super paramagnetism. And there is this big confusion between the paramagnetism. What is the difference between super paramagnetism and paramagnetism? Right? So the first similarity is they both will show some magnetization when you apply magnetic field. I will write H now because so if I apply H, they will react. Both will react. Okay, and the strong reaction will be shown by this guy. This is a bit weak reaction, because in super paramagnetism everything will get aligned in a single direction. But in paramagnetism, not every spin will get aligned. Some spins may not get aligned. So even if I compare the best state where all the spins are compared in paramagnetism, and when I apply now the third, now the differences the differences starts. Okay, the differences. So whenever you apply, now I try to increase my temperature. So application of temperature. Now if I try to increase my temperature, everything will get destroyed. My whole magnetization will get destroyed, but not in the case of paramagnetism. Yeah, magnetization will get destroyed, but not to the extent as in superparamagnetism. Okay, so the main difference is this temperature application. Whenever you apply temperature, whenever you try to give some energy, these spins will just disorient or orient in some random directions, and they will start destroying the magnetization in a very large values when compared to the paramagnetism. So that is the main difference between the superparamagnetism and paramagnetism. Okay. So superparamagnetism is mostly about a single domain. And again, what is domain? So coming to that. So just like in material science, you have grain, you have crystallite. Crystallite is nothing but all the atoms are perfectly obeys the symmetry there in perfect periodicity. Okay, that's the best part rather than saying symmetry. So in a crystallite there is a perfect periodicity of atoms, and the same goes for domain. In domain you have perfect periodicity of your spins. Okay, and again, grains will have grain boundaries, domains will have domain walls, and grain boundaries will obstruct the dislocation motion, that means the plasticity. The same goes for your domain walls. Domain walls will obstruct your the spins to align in your magnetic field direction. So that is again one thing. And whenever you start decreasing your grain size, the domain size will also start decreasing. And whenever you decrease the domain size, you are increasing your domain walls. So okay. Instead of saying in air, I will just write it. Okay, that will be much more proper. Okay, so this thing you have seen, right? I hope you guys have seen this. Oh, it's not M, right? M. It's HC, coercivity. It is HC, not H. It is HC. And this is my grain size. So whenever I start decreasing my grain size, that means, see, and please remember, there is no good correlation. There are correlations, but there are no exact correlations between the domains and grain crystallites of grain size. Okay, so there are some empirical correlations, but there is no like exact correlation. Now, suppose I have a big grain, right? Suppose my grain size is very large. Inside grain size, I will have domains, just like the grains, polycrystalline grains. I will have domains inside a grain itself, inside a single grain. Okay. Now, whenever if I try to apply magnetic field, this guy, for example, this guy will try to align, but if this guy, this domain wall will give an obstruction to the rotation of these spins. So that's why whenever I try to decrease the grain size, this is single domain, this is multi domain. Now what's happening is, whenever I'm trying to decrease the grain size, my HC will increase, right? And after reaching certain value, there will be a single domain. You cannot have all the domains. It's not like Hall pitch correlation. You are just decreasing your grain size, there is more and more number of grain boundaries are there, and then you will have this thing. So whenever you try to decrease the grain size, yeah, sure, the domains will also try to increase. Then you will have a multi-domains. There will be more domain walls. But after reaching certain value, after reaching certain grain size, your domains are so small, or your domains are getting so small, they will become a single domain in contrast. Okay, so whenever you have a single domain, then it's nothing but all these particles, if you apply magnetic field, they will just align in one direction. It will become a whole single grain such that they all will align in a certain direction. Okay, so please remember this. It's not like whenever you try to decrease the grain size, everything is becoming one domain. No, the domain size will decrease. Instead of saying that, I will write it. See, now if I try to decrease my grain size, so my domains will start decreasing. I mean, the number of domains will increase. I cannot draw everything, right? So number of domains will increase, and these domains will get so small, it is easy to align them in a single direction. And that is what happens in superparamagnetism. Superparamagnetism, they have domains, but they have multiple domains. See? So superparamagnetism, nothing but whenever you have a nanoparticle, see, if you have a nanoparticle, each particle will have some grains. Okay, either it is a 1 grain or 2 grain, right? And the grain size is very small. And each grain will have magnetic moments, will have domains, and they have their own magnetic moments. Okay, and then you will have a single domain. See, these, if you see wholly, you will have so many domains, but they will combine to become a single domain, right? Okay, and then you have a highest coercivity at one point, but your coercivity will start dropping. Why? Because of this guy, superparamagnetism. That means the temperature will start acting. That means, again, whenever you decrease your grain size, you will have more surface atoms. That means the more the surface atoms, more is the surface energy. So even if you give a little bit of thermal energy, this surface energy, I mean, your system already has some surface energy, and then you are giving thermal energy, the system will become unstable, right? So the surface atom, the surface spins will get distorted, more or less, if I explain. And because of that, you will lose your HC, the coercivity, right? So yeah, that is what's happening. That is what happening in here, the domain size, grain size distribution. And sir has explained the exchange interaction, and I don't think so there is need for the exchange interaction. Again, I have explained this. Exchange interaction is purely quantum mechanical term. You cannot explain it physically. People have tried, so the best explanation is the exchange interaction is a combination of electrostatic interactions electrostatic interaction and symmetrization postulate. See, electrostatic interactions is a physical thing. You can clearly explain. But symmetrization postulate, no, you cannot explain it because it is coming from the parity operator. It is coming from the fermions. Whenever you apply the parity operator to a fermion, it will give a negative sign. Right? And to get that negative sign, then you should have a antisymmetric term. So one should be symmetric, the another should be antisymmetric term. So when I am saying that symmetrization postulate, so whenever you write a wave function of any electron or electron, okay, not about any electron. So if you write a wave function of an electron, you have these quantum numbers, right? So first thing you will write the spatial distribution, and the spatial distribution is coming from the orbital magnetic moment, the spatial distribution, the orbital moment. The second one is your spin, right? And that is the spin magnetic moment. So whenever you have wave function, you are writing the spatial distribution and the spin. These two terms should be there in your wave function. If you are trying to solve any Schrodinger wave equation, your wave equation of an electron should have your spatial term, your spin term. And when you apply a parity operator, it will give a negative term. It will give a negative sign. And negative sign can only come if either your spatial distribution is symmetric and spin should be antisymmetric. What do we mean by antisymmetric? Antisymmetric is nothing but one electron should be up, another electron should be down. That is antisymmetric. Symmetric means both should be up or both should be down. Right? So that is symmetrization postulate. So whenever I apply parity operator to a wave function of an electron, either my spatial distribution should give me a negative term, it should be antisymmetric, or my spin should be. But still, if you have any doubts, you can ask me. I can even share notes regarding this. I can even share the lectures actually, if you want to know more about how this exchange interaction plays a big role in your ferromagnetism. Okay, not even ferromagnetism, and many things. So that's all about the magnetic properties. Now moving on to so moving on to optical behavior, right? And yeah, I have mostly explained this optical behavior, like the surface plasma resonance. I have explained it many times, right? So I will not explain the SPR, so the surface plasma resonance. So I will only explain about these block waves, and also the how do you absorption these things, and also the physical optical properties. So I will explain why the metals are transparent, why some metals are transparent, and also how does light goes through your dielectrics, and then we will understand what is fluorescence. Okay, yeah, that's all. And also I will explain about exciton, right? So how the excitons happen, right? So before moving into this thing, we need to know what is the energy gap between your conduction and valence band. Just like here, you have your valence band VB, and then you have your conduction band CB. Now this is my band gap. Okay. Now if you supply some energy in a light form mostly, so you radiated this metal with some light, with radiation. Okay, it might be any type of radiation. It doesn't matter. And let's say it has an energy of h nu. Okay, each photon inside your radiation or each energy packet will have an energy of h nu. Okay. Now, I will not explain the absorption, reflection, these things because you people already know, right? I hope I need not to explain these things because it's not very complicated, right? It's very easy. Absorption, transmission, refraction, reflection. These are the four terms we use. Okay. Now, this is my energy h nu, and this is my band gap of energy E1. Okay. And if you have a band gap, then those things are called as semiconductors, right? Because in metals, so before going to that, let's have a brief recap of what we have did in the band gap, right? Orbital molecular theory. So we have discussed that whenever you have some gap, a little gap between your conduction band and valence band, then they are called as semiconductors. And their if conduction band and valence band is very small, like very tiny, and also in some metals it will overlap. In some cases it may even overlap, which is the cases for metals. Okay. Now, for some materials, let's say my band gap is 0.5 electron volts, which is low, and insulators, the band gap is very large. So let's discard our insulator. Okay, let's take some semiconductor types. Or the band gap is between how do I say 0.5 to 0.8 electron volts. Okay. Now I am trying to emit some radiation onto this material. Let's say this is my material, and applying some radiation of h nu, and it has an energy of, let's say, 0.6 electron volts, and there is another radiation which I will apply after this, which is 0.2 electron volts. Now, whenever I try to apply 0.6 electron volts, and because the band gap is what, 0.5, or let's say band gap is 0.6 electron volts, and I am applying 0.6 electron volts of radiation, then what happens? The electron in my valence band will take that energy, which is 0.6 electron volts. It will jump into conduction band, right? And then it may even conduct electricity, or it may even emit something. So let's forget about what it does after. Okay, we are only concerned about what is happening right now. So electrons enter into our conduction band. So what's happening here is whatever the energy that you are supplying, 0.6 electron volts, is being absorbed, not adsorbed. Okay, is being absorbed. So that is what we see in metals. So metals have very low band gap, and some band gaps, and sometimes even in some metals there is even the overlapping of conduction band and valence band. All the radiation which you are trying to show onto a metal is getting absorbed. That's why whenever you try to torch a metal with your light, or whenever you try to take a torchlight and emit some light onto the metal, it will not get transparent. This is the reason. The reason is whatever you are trying to hit with your light is getting absorbed. So that's why the metals are not transparent. But in some insulators or in some semiconductor, some insulating materials, the band gap is very much closely related to the light. Then whenever you try to, sorry, not light, in some insulators, or mostly the insulators you see like glass, okay, in some or more materials, which of which if you do not have the certain band gap that satisfies your radiation, then those photons will just pass through, okay, because electrons are not interested in taking that energy, because they need high energy, right? And the light doesn't have that much energy, because the light has very small wave, sorry, not wave, very small, yeah, very small wavelength, not very small, very high wavelength, right? Am I correct? Because energy equals to h nu. If energy increases, the frequency increases. If the frequency is inversely proportional to wavelength, if frequency increases, wavelength decreases. Sorry, shorter wavelength. Yeah. There's always this confusion between. It's better to have your equations rather than remembering things, right? So they have very high wavelength. So if your wavelength is very large, then you have less energy, and if your wavelength is very small, then you will have very high energy, right? So now, okay, so we know we have created an electron, so we have created a photon which is irradiated onto a material, and the electron has jumped. So first, at time t equals to t0, this is the conduction band. I will not write conduction, I will write just CV, this is valence band. This is my electron. Now the photon falls on it at time t equals to t1. The electron has jumped into the conduction band by absorbing that electron. Now there is a hole. We all know, we have long studied semiconductor physics. So whenever an electron come out from an orbital, we will have a hole there, right? And that is given as valence band. Right. Now the next case is, now this electron will have negative charge, the hole will have positive charge. Or I shouldn't say positive charge, but it doesn't have any charge, okay? So this electron and hole pair will have an interaction, and they will bind, they will get binded, right? And this binding energy, and there is also this binding energy, and if you combine, and if you have a wave function of an electron and hole, then that is called as an exciton. That's all. Now, the electron will not go away because the hole is binding it. The same goes for hole. Okay. So then you will have this binding energy also, which makes the electron to stay near to the hole. And you people may confuse, what is this? Right. So because we have a sharp conduction band and valence band. Again, whenever you try to decrease the size of the particle, this conduction band and valence band will disperse, right? Because the atomic orbitals are missing in a band. Then what happens? These energy values will not be, they will get discretized, right? And that's why you will have energy values here too. And the same goes for this guy. You have discretized energy levels. Now the gap is small. This is the band gap. This Bg2. If we are talking about bulk, then this is my band gap. If I am talking about nanoparticle, this is my band gap. Right? So because of that, your band gap gets reduced. And if my photon, if you even take light, and because the band gap is low, the energy to move my electron from valence band to conduction band is low, then even the light, the normal light can do that thing, can do that job, right? That's it. That is about this photon and this exciton. And because of that, you have your electron. So there is jump of electron from here into here. And you have your holes here. Okay, so there is this interaction between them, and this interaction is given as binding energy that binds this electron and hole. Okay, so this is what happens. And yeah, same, the valence band, the conduction band, the exciton levels, and we people call it as an exciton levels between what is the energy from this valence band, and this is E1, from here to here it will be E2, from here to here it will be E3. And these are the different exciton levels. That's it. And decreasing with size, you will have different absorptions, right? So if I have, this is like increasing the particle size, sorry, decreasing the particle size. Because whenever I try to decrease the particle size, these levels will come closer. You will have different levels, and when you have different levels coming out, then you can easily excite your, or you can easily have an exciton, right? Because there is more discretization coming into picture. So that's what happens here. And then yeah, so coming to surface plasma resonance. Okay, so what else is there to explain? Yeah, there is this term, how does we know why the light doesn't go through the metals, so that thing we know, because the conduction band and valence band sometimes overlap. Even if you supply very high wavelength things, the electrons will just move from conduction band to valence band to take by taking that energy. So that's why nothing will pass through, everything will get absorbed. Now, what about how does light get through dielectrics? That is also a question, right? So now, and the main reason that the radiation of not all the wavelengths, only certain wavelengths can enter a dielectric is because of its Fermi level. Okay, and the Fermi level lies at the top of the valence band, which is just below a band gap. Okay, so let me explain how it is. Let's say if I have many empty levels, this is my valence band, okay, and this is my, so sorry, this is the conduction band, right? And this is my valence band. Now, in dielectrics, what is Fermi level? Fermi level is nothing but that is the, in probability I can say, that is the most probability energy state or level where you can find most of your electrons, in that system or in that energy level, right? It's like most preferable energy level, the most, or more or less, it's like you will find most of the electrons in that energy level. Okay, so that is about the Fermi level, and yeah, so if my Fermi level is this, just above the valence band, this is my Fermi level. These are field levels, okay? And because of Fermi level, most of the electrons are lying here, not on this. I mean, electrons will lie here also, but less when compared to this Fermi level. Okay. So now, what is the band gap? Band gap is just this guy. If I am talking about the electron here, then my band gap is very large. Here to here, delta E gap 2. This is 1. Now you will are getting that figure, right? I mean the idea. Let's say this is my conduction band. So electrons will just jump from here to here, and you will have hole in your Fermi level. And this is your ground state, and this is your excited state. And again, the electron will come to the ground state by combining with hole and giving out some photon, which will again return to the ground state. Okay. So now you know the reason behind the radiation of because how the light get through the dielectrics. So only the radiation of certain wavelengths it happens because of this Fermi level, which is lying just above the valence band and below the conduction band. And we know the conduction band has very vast amount of orbitals which are of empty levels above it. Now to excite an electron, access the gap requires a photon which should have at least an energy of delta E gap. Okay. Thus the radiation with photon energy less than delta E gap cannot excite electrons. So if my photon of greater than delta E gap comes, then if my photon comes and hits this electron with energy greater than delta E gap, then only it will go to the conduction band. And if it is greater than delta Eg, then the other part of that, I mean the remaining part will be converted into kinetic energy. Okay. So again, let's not worry about that. Let's not worry about how much kinetic energy. Okay. So if it is less than delta E gap, then it will not get absorbed. We all know that. Thus the radiation with photon energy less than cannot excite electrons. And the material will just transmit that photon. Okay. Now, if the photons with the band gap energy greater than delta Eg gap, then the photons will start getting absorbed. Right. So then the material become opaque, just like metals. Then it will act as a metal. Thus, if I give an example, most of us have seen this backlight, right? When you know backlight, right? Most of the people know backlight, where the backlight is used, right? So when you have a gypsum and you do the water of crystallization, you will get the backlight. No, it is different, right? Gypsum and backlight is different. Okay, let's not worry about the chemical properties. So if you take a backlight, so backlight is transparent if you irradiate with the infrared light. So whatever the infrared light, so if I have a backlight, and if I show it with the infrared radiation, we all know where the infrared radiation lies, right? UV visible infrared, right? Which has higher wavelength when compared to your visible light, right? So UV will have less wavelength when compared to your visible, and infrared will have higher wavelength when compared to visible. So you know that this radiation spectrum, right? You will have gamma rays, and then you will have X rays, and then alpha ray, beta rays, then X rays, and then you have UV rays, then you have visible, then UV visible, and then you have infrared, and then you have radio waves, and you have gravitational waves. Yeah, I mean the radiation goes on and on. So yeah, where were we? Yeah, backlight. So whenever you have backlight and you irradiate with infrared, it will just pass through. It is completely transparent to that guy, to the infrared radiation. But if you irradiate with visible light, white light, or the visible light, the sunlight, then the backlight is totally opaque. Then a backlight visible, it is opaque. It acts as a metals, okay? It is transparent. It is infrared. Now you people understand, right, why some dielectrics act as opaque at some times, transparent at some times. Opaque happens only if your photon energy is greater than or equals to the conduction band energy. And transparence happen if your photon energy is less than your conduction band. That's it. These are the two things you see. Now, colors. How the materials appear in different colors. Again, that is one question, right? So, whenever you see like a green color, now why do you see in green color on leaves? Yeah, we all know that there is a chloroplast, chlorophyll, and chlorophyll takes this radiation. So why? So again, the same goes for delta E, the band gap. So if a material has, let's say, a band gap with energy delta E gap, so let's say an unknown material, let's say material, we don't know what it is, just take a material, and it has a band gap of this much. And let's say this lies within the visible spectrum. So we know VIBGYOR, right? Violet, indigo, blue, green, yellow, orange. Yellow, green, orange. Okay. So this has some wavelength, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6, 7. And corresponding that I have E1, E2, E3, E4, E5, E6, E7. So each color has certain wavelength, and each wavelength then will have certain frequency, and that frequency means it has some energy, which can be related as E1 equals to hc divided by lambda 1, and c is the speed of light, because we are only talking about photon. Okay, so if you are talking about electron, then it will not be c, it will be v. What is v? V is the velocity of electron. So radiation has the speed of light, so that's it. If you are talking about any particle, then it should be, instead of c, you should write the velocity of that particle, not the speed of light. Okay. And because we are talking about radiation, we are talking about only speed of photon, which is equal to speed of light. Now, if a material, again, this material has certain band gap, delta E gap, and let's say it lies this energy Eg, delta E gap is nothing but Eg. Let's take the constant Eg. It lies between E1 to E7. Let's say E1 less than Eg less than E7. It lies between E1 to E7, and we don't know where it is. Okay. So now the wavelengths with energy greater than this are absorbed, and those with energy that is less are not. What do you mean by that? So let Eg will have some wavelength lambda g. Again, the wavelengths with energy greater than this are absorbed. Let's say my Eg will lie here between E3 and E4. Right? So all these guys will get absorbed, E1, E3, E4, and all these guys will get transmitted. I hope you are able to understand. So Eg is nothing but the band gap of this material. Okay. So E1, E2, E3 has higher energy when compared to Eg. E4, E5, E6, E7 have lower energies. So all these will be transmitted, and all these will be absorbed. And the absorbed radiation is re-emitted with the excited electron. Again, this will be re-released when the excited electron will drop back to its lower energy state. Right. Now what happening here is, so whenever this absorbed energy is taken by the electron, it will move to the excited state. We all know that, and then it will again come back to the what do you call the ground state, and this takes in picoseconds. It is very fast. Okay, it's not even slow, so it's very fast process. And yeah, electron will come back to its ground state, and it will again emit the photon. Now this photon that it has been emitted has a different wavelength than the energy that it has absorbed. Right. So now whatever the emitted that has been absorbed is emitted as a photon, and that is the characteristics for the your color. So for example, if my material is made up of, let's say my material is some sodium carbonate, anything. Okay, so it has band gap energy of Eg, and that Eg lies between E3 and E4. Good. Now all the energies above this one are getting absorbed, and all the energies below are getting transmitted. Okay, whatever the energies that are absorbed are getting absorbed by an electron, and this electron will again come back to its state. So first E1 plus E2 plus E3 are getting absorbed by electron, are getting hit. So this electron will jump, and then it will come back. And when it comes back, it will emit a photon. And this photon is a mixture of violet, indigo, and blue. And they will undergo the diffraction. Because of that, we will have a different color, a characteristic color, a mixture of violet, indigo, whatever the color it forms. Okay. Now what people try to do is, they will add some impurities. For example, if I am adding in wafers, like semiconductor wafers, if I try to add some impurities, and because of these impurities, there is a creation of an extra energy level here. Okay, you have conduction band, valence band, there is another band in between this. So whenever I try to hit, first the electron will go into valence conduction band, this conduction band, this is okay, go into conduction band. It will not directly go here, it will first come here. I will write it in red so you people can know the difference. So it will first go here, it will not directly come here down, it will come here first. In that process it will emit a photon of E1 and again it will come here. In that process it will commit again a second photon of E2. So there are two photons that are coming out. And this happens, and if this thing happens then there is a different color. Actually it should show some color of C1, but now because of this doping and because there are two photons that are emitted, they undergo diffraction, and because of that you will see a color C2. So that is what happens. Okay, so deliberately we introduce impurities to mess with the band gap, and because of this messing with the band gap, the radiation will absorb as same as before, but it is now re-emitted into two discrete steps. So first with electron energy E1 and second with electron energy E2. So particularly pure colors are created when glasses are doped with metal ions. Okay, so whenever you dope glass with metal ions, so whenever you will have a pure colors, like for example if you dope your glass with copper, you will have a blue color, and if you dope your glass with cobalt, it will give violet color, and same goes for chromium, it will be green, and for manganese it will be yellow. So it depends upon what type of metal you are doping, because each metal has its own band gap, so not the band gap, so that band gap is getting changed here, right? And if you change that band gap, you will have different color. That's it. That is the whole color behavior of the atoms we see. Now people have seen what is fluorescence. Fluorescence is nothing but the photon, so first we will talk about luminescence instead of fluorescence, because you need to understand, right? Let's say if I'm talking about luminescence, okay? Now, electrons, we all know electrons can be excited into higher energy levels by the photons and provided by their sufficient energy. Now, energetic electrons, just like in cathode ray tube, do the same. In most cases, the time delay, just like I have said before, whenever you is the ground state, is the excited state, again is the ground state. So whenever you show, let's write like this, so electrons travel. So this is my photon which is falling, and because of this the electron will jump from here to excited state, and again it will jump back to ground state. So again it will emit photon, right? If now, and we all know what we have seen so far, this happens very fast, right? Electron comes, hits the electron will jump to excited state, and from there it will again jump back to ground state. It will happen very fast. Okay, so T is for T1, for black, T1 is fast. Now, if on dropping back, the photon they emit is in the visible spectrum. That is called as luminescence. Oh, my bad. So this is what we see, right? That is not luminescence, okay? So this is what actually we have seen. Now, T1 is fast, okay? So what about, let's take yellow, okay? So again, same radiation hits. Now, instead of, so see, this excitation happens fast, but instead of coming down to ground state, it stayed in excited state for a bit and then it came back. T2 is moderate, it's not fast, it didn't happen as fast as first one. And if this emitted photon is in visible range, that is called luminescence. So whenever you show the light and the material starts radiating some light, okay? So whenever, if I take a material and I have shown white light and it starts radiating green color, okay? Even if I turn off my light, the material still glows in green and it will continuously and starts fading away. See, there is this delay. Even if I take out the light, the material still radiates, but for a short amount of time, because the electrons are coming back to ground state, right? That is called as luminescence. Now, so the material continues to glow for some time, even when the incident beam is removed. Now, when the time delay is fraction of seconds, so if my time delay is fraction of seconds delay, okay, this is delay. Delay is fast, there is no delay, so let me write it, not fast, okay, no delay. I will make a table, right? That will be better. Type delay, okay, luminescence, moderate delay, and photon emitted is in visible spectrum. This is in visible spectrum. Now, fluorescence. Again, there is a delay of fraction of seconds. Then you call it as a fluorescence. When the time delay is fraction of seconds, it is called fluorescence. So again, used in fluorescence lighting, where it is excited by ultraviolet from a gas discharge and TV tubes, where it is called as a scanning electron beam. When the time delay is even longer, time delay is even longer, then that is called as phosphorescence. See, we have seen in phosphor screens, cameras in previous, the old cameras, they used the phosphorus screens. Even some cases like electron beams also use phosphorus screens, where the delay is so large. Okay, so yeah, that is about luminescence, fluorescence, phosphorescence. Luminescence is nothing but if the delay is fast, if the delay is not slow, not very slow, so then that means it is moderate, and the visible and the photon that is emitted is in visible spectrum, then that is called as a luminescence. And if there is a delay of fraction of seconds, then it is called as a fluorescence. And if you have a phosphorus, if you have a delay of even longer than fraction of seconds, then you have phosphorescence. Just like in phosphor screens, few people have seen used. Okay. So yeah, that's all about today's lecture. And even in Michael F. Ashby book, this is the max they have discussed. Okay, so how the colors thing we see in metals, dielectrics, insulators, and how do we see colors? Yeah, that's all about the optical properties of nanomaterials. That's all they have discussed. So we will stick to that. We will not talk more than that, because more than that will be too much, right? Not too little is bad, not even too much too little is bad, too much is bad, right? So let's stay in between that gray area. Okay, so that's all about today's session. If you have any doubts, you can stay. I will stop the meeting.